Okay, so in the Ontario curriculum, I think some schools actually have taken this out. Because it's mostly because implicit differentiation is a derivative technique for non-functions, such as, do you guys know what that is?
Circle.
Right, is a circle a function? No, it's not a function, right? So if I ask you to find the derivative of the circle, okay, let's say at that point, do you see that, like, let's say this is okay, at the origin, let's say this is like 0.7, okay? Do you see that if I plug it in here, I should get two slopes, one here and one here? Unlike, because it's not a function. Usually if it's a function, it'll only have one, right? But because it's not a function, it'll have two slopes. Now, if you're to do this in the traditional explicit differentiation, meaning isolate dy, you get this. You get two functions, plus or minus of 1 minus x squared. Okay, instead of doing it this way, you can see that this actually leads to an ugly differentiation too. Okay, and it gets even more complicated later on if you have things like xy squared plus y cubed is equal to 1. This we don't even know how to really isolate y here. Okay, so this right here, like if you're differentiating this form right here, is called an explicit differentiation. So what we've done so far is called explicit differentiation. Instead, what we think of this is this. We think of this as an x squared, a function of x squared equals 1. That's how we think of it. That's true, right? Y is a function of x. Y is somehow related to x, right? And this is what we do. We differentiate this. This is going to be 2x. So if you differentiate that in terms of x, it's 2x. How do you differentiate an expression that looks like this? What's the first thing that's being done to x? F. The second thing? Square. So you would do the square first like this. Wouldn't you? And then you have to chain it, right? Now remember f was y, right? So let me rewrite it in terms of y. You get 2y dy over dx. Okay. So I just wrote it this way to make it clear to you that this is an implicit differentiation. But look, could you go from here straight to down here? So differentiate the x squared, you get 2x. Differentiate this, it's 2y, but y is a function of x, so you got to chain it by dy over dx. And then it equals to 0. Okay, so I'm doing the exact same thing here. Usually we don't write this, we go straight from here to here. Okay, and then what you do is isolate dy over dx. Okay, so first of all you get minus 2x, and if you isolate dy over dx now, you get minus x over y because the 2 will cancel out. Now, when you do implicit differentiation, your derivative function is both in terms of x and y. Okay, x and y. So if I ask you to find the slope at x is equal to 0.5, it's not good enough that I have x. That's a bad part of implicit. I actually need y too. So where am I going to get the y value? Yeah, you have to plug it back into this original equation. So this is extra step. Okay, so you're gonna get y is equal to plus or minus of 1 minus 0.5 squared, which is gonna be plus or minus root 3 over 4, which is the same thing as root 3 over 2. So that means we're gonna get two slopes. Okay, so when we're talking about 0.5 or half and root 3 over 2, the slope is, right, it's going to be half over root 3 over 2. So you get minus 1 over root 3. Okay. Another slope. When it's half and minus root 3 over 2, the dy over dx is going to be positive 1 over root 3, right? The sign just changes. So two slopes.